So this is Contracts with Private Cost per Unit of Effort. My name is Tal, and this is joint work with Paul Duetting from Google Research and Inbal Talgam-Cohen from the Technion. So think of a brand that uses platform like Upworks and hires influencer to create sponsored content and drive traffic into the brand's website. This requires some level of effort from the influencer, and naturally, different levels of effort would bring different outcomes in terms of quality and quantity of the visitors to the website. So maybe putting in 1 unit of effort, which may capture one quick story with a brand's product, is not likely to bring any targeted visitors, but putting in 10 units of effort, putting in hours of taking photos, is likely to do so. Usually the brand is not willing or not able to monitor the influencer and observe the exact amount of effort he puts in. Rather, he observes some stochastic resulted outcomes, say the quantity of visitors, and pays the influencer for his effort accordingly. So up till now, we've described the classic principal-agent setting of Grossman-Hart, where there is an agent, in our example, the influencer, that performs a task for the principal, in our case, the brand. The principal uses a contract, a payment scheme to incentivize the agent to take a certain action. However, the exact action, the exact effort level taken by the agent is privately known to him. And this feature is known hidden action. So to incentivize the agent, despite of that, the principal relies on stochastic outcome generated by this action. And these stochastic outcomes serve as the noisy indicator and also used for the payment for the agent. It is natural to think of agents as being more or less qualified, having different abilities, different types, and the types may be privately known to them. So such an addition of types immediately puts us in the realm of mechanism design. So we have a natural setting with both contract design and mechanism design, and this is what we're interested in our work. I will mention 2 recent papers that consider contract design with typed agent. The first one is by Chade and Swinkles. They study a setup that is similar to others but make different assumptions and do not focus on computational efficiency. The second is by Guru, Ganesh, Schneider, and Wang that also appears at EC. They are the first to consider the combination of hidden type and hidden action from computational point of view, but they have a model that is different from ours. Types in their works are modeled by multidimensional vectors, and they show hardness of several design problems. Other less related work that also differ from ours in their focus of multidimensional type is the classic work of Myersonian and the work of Gottlieb and Merera. So it is well known from action design that single parameter types may allow positive results even when hardness results hold for multi-parameter types. And one of the simplest single-dimensional types you can imagine is described by a single number, specifying how costly is 1 unit of effort for the agent. So a weak influencer may have opportunity cost of 30, whereas a strong influencer may have an opportunity cost of 10. So our main question is how to design contracts that incentivize the agent to take the desirable action now that we have private types. Whether or not we can overcome hardness introduced by Guru, Ganesh, Schneider, and Wang, and perhaps we can use well-known mechanism design results, such as Myersonian theory, for our single parameter model. So for the remainder of this talk, I'm going to get into the following concrete model and do some analysis. So an instance of our model consists of 2 players, a principal and an agent. The agent has a set of n actions available to him. Action I requires gamma I units of effort from the agent. An action leads to one of m rewards for the principals. Specifically, action I induces the distribution fi over the rewards. We denote the expected reward of action with capital R. The agent has a type C, which is a non-negative number that captures the agent's cost per unit of effort. So when the agent takes action I, the total cost he bears is gamma I, the amount of effort action I requires, times C, the cost per unit of effort of this agent. Types are drawn from a distribution G, and the support of the distribution, the set of all types, is denoted with C, and it can be either continuous or discrete. So the instance itself is publicly known, but the action which the agent actually takes is hidden from the principal, and this is called hidden action. And the agent's realized type is also privately known to the agent. This is called hidden type. So our notion of a contract actually generalizes the standard one since we accommodate it for agent's type. So a contract XT is composed of an allocation rule X and a payment rule T. It gets type report C tag from the agent that need not necessarily be his true type. The allocation rule maps the reported type to a recommended action, and the payment rule maps the reported type to a vector of m payments, one for each outcome. Now, a key property of the allocation rule that will play a role in our results is monotonicity. So a monotone allocation rule maps costly actions to agents whose private cost is lower, and intuitively, such agents are better suited to take effort-intensive tasks. So every contract, XT, induces the following two-stage game. Stage 1, the agent submits type report C tag, fixing the payments and the recommended action. On stage 2, the agent chooses an action I, which need not necessarily be the recommendation. Then he incurs the cost of gamma I times C. An outcome J is realized according to the distribution Fi, and the principal is rewarded with Rj, and he pays the agent according to the fixed payment Tj. Now, to talk about incentives, we need to talk about utilities. So the agent's utility is the payment minus cost, and the principal's utility is the reward minus payment to the agent. Using the same notions from earlier, we can write down the expected utility, where the expectation is over the random outcomes. And note that the sum of players' expected utility is the expected welfare, which is the expected reward minus the cost of the agent. Now, since the agent is rational, he chooses a report and an action that maximizes his expected utility. We say that a contract is incentive compatible if the utility for every type is maximized on truthful reporting and taking the prescribed action. I will mention that focusing on incentive compatible contracts is without loss of generality by the revelation principle. And now that we have the definition of incentive compatibility, we can add another key property of an allocation rule. So we say that an allocation rule is implementable if there exists a payment rule T such that the resulted contract XT is incentive compatible. And our goal throughout this talk would be to take the head of the principle and design incentive compatible contracts that maximize the principle's expected utility, where the expectation is over the agent's random type as well as over the random outcome. So just to give a brief overview of what we're going to see, we give a characterization of implementable allocation rules for this model, which applies to both discrete and continuous typeset. This characterization shares important features of Myerson's celebrated characterization result, but it also departs from it in significant ways. Then we present two applications. One is a polynomial time algorithm for finding the optimal contracts where the number of actions is held constant. And other is the Myersonian approach to find the optimal contracts for uniform distributions. So one of the most useful tools for a single parameter mechanism design is Myerson's theory. This theory provides a characterization of implementable allocation rules, which says that an allocation rule is implementable if and only if it is monotone. We showed that this lemma fails for our setting by providing an example for monotone allocation rules that is not implementable. And the proof is technical. It follows from writing down the incentive compatibility constraints and show that they lead to a contradiction. But I do want to mention that this negative result is inherent in the combination of both hidden type and hidden action. And it not just follows from the fact that sometimes in contract theory there are actions that we cannot incentivize, So to be more specific, if types were known in this example, and it was a pure contract theory problem, then we can show that there exists a contract that incentivizes this allocation rule. So we overcome the challenge of combining the two fields of hidden type and hidden action by presenting a characterization of implementable allocation rules that incorporates both Myersonian and the contract theory characterization of implementable actions. So we begin with the discrete case. Fix an allocation rule. The characterization incorporates these lambda weights, which represent joint deviation planes of the agents from the allocation rule. So whenever the true type of the agent is C, then with probability that is proportional to lambda C theta k, it pretends to be type C tag and takes action K. And an allocation rule will be implementable if and only if there exists no deviation plan that satisfies the following. First is weakly dominant distributions. So the generated distribution of each reported type matches the distribution of the non-deviating truthful type. Second is strictly lower joint cost. So the joint cost of the deviation plan is strictly less than the joint cost of the allocation rule. So intuitively, an allocation rule is implementable if and only if there exists no deviation plan such that the agent gains the principal, get him to think that they act according to the allocation rule, but they do it with lower cost, so they save cost as a group. So we know that monotonicity does not suffice us, but it does play a role. And while not every monotone rule is implementable, every implementable rule has to be monotone. And the proof is very simple. The idea is to take two types, low and high, that violate monotonicity. Low takes the low effort action and high takes the high effort action, and consider the deviation plan where they both swap. This leads to the same distributions, but because of better balancing of the task, to a lower joint cost. And now, as for the proof of the characterization, it follows from taking the dual of this linear program. This program finds a contract that implements X, and since it has a polynomial number of variables and constraints, testing the implementability of an allocation rule can be done in polynomial time. And by changing the objective, we can also show that computing payments that maximize the principal's utility can also be done in polynomial time. So this is for the discrete characterization. And now we tackle the challenge of characterizing implementable rules for the continuous type set. For this, it will be instructive to look at an allocation rule graphically. So we have two dimensions. On the x-axis is the type, and on the y-axis is the effort level allocated to the type. And the allocation rule can be any function from this infinite domain of types to the set of effort levels. And in light of our discussion before, this is not surprising that we can also show that in the continuous model, monotonicity is required. So every allocation rule has to be monotone. And then, because the image of X is finite, the only allocation rules we need to consider are those who are monotone, piecewise constant, with at most n pieces. Now, the key ingredient for the continuous characterization is the set of n breakpoints induced by the allocation rule. We're going to use it for a reduction to the discrete model. We show that determining whether or not X is implementable in the continuous model actually reduces to determining whether or not X is implementable in the discrete model, where the set of breakpoints is the set of types. And there is the following added constraints on payment, which I won't get into now, but I will mention that adding this constraint does not change the tractability of the characterization, so we can conclude that for a given monotone piecewise constant allocation rule, determining whether or not it is implementable can be done in polynomial time. So now that we have both continuous and discrete characterization, we present two applications that extend our theory and use our characterization. So the first is for the discrete type set. We give a polynomial time algorithm for computing the optimal contract when n, the number of actions, is held constant. And I won't get into the proof, but I will mention that this simple positive result demonstrates the power of single-dimensional model, since in the multi-dimensional model of Guru, Ganesh, Schneider, and Wang, they show that computing the optimal contract with a constant number of action is hard to even approximate. Now returning to the continuous model, we'll give an example of a divide and conquer separation between hidden type and hidden action. The idea is to ignore the constraints of hidden action. This brings us into Myersonian land, where we can apply the rest of Myerson's theory. We show that Myerson's payment identity hold and that the expected revenue is equal to the expected virtual welfare, where this is the virtual cost. Then we consider the virtual welfare maximizing allocation rule, bring back the hidden action, and ask whether the result of Myersonian that the virtual welfare maximizing allocation rule is implementable hold in our general setting with hidden action. What we show is that the answer is yes when the distribution of our outcomes, when the distribution of our costs, is uniform. So very quick high level of idea of the proof. If X is not implementable, there exists a deviation plan with matching rewards, since we have matching distributions, and lower joint cost. And since in uniform distributions, the cost and the virtual cost are proportional, so lower cost mean lower joint virtual cost, which is not the case for exponential distribution per se. We have that the deviation plan gives a higher virtual welfare than the virtual welfare maximizing rule, which is a contradiction. So just to quickly wrap up, we propose a natural principal agent problem with hidden action and single-dimensional private type, which seems to strike a balance between applicability and tractability. Provided analog to Myerson's theory, two characterization results, one for the continuous and one for the discrete type set, on which the agenda of this intersection between contract theory and mechanism design can be built. We provide two proof of concepts which seem to show that this redirection is promising. First is a much more positive computational result than the corresponding result of multi-parameter types. And the second is a non-trivial divide and conquer result, as we explained earlier. Interesting direction going forward would be computational, finding whether or not we can compute the optimal contract in the discrete model in polynomial time, and verify or disprove the divide and conquer approach for other distributions than uniform. And this is pretty much it. Thank you so much for listening.